Day 36, Honors Physics, Newton's Three Laws, Example 20. So here I'm getting a little fancier with my drawing. Well, you could draw the car as a rectangle. Mine is not that fancy, but there's the car. It weighs 15,000 newtons. Taking the shortcut, 10 times 1,500 gives you the weight. And the road support force is 15,000 newtons up and down. There's no acceleration up and down. Once again, noticing I'm not really paying much attention to where I'm actually putting those forces. They're actually applied to the four tires. You don't need to get that involved. But we do know that there's a 15,000 Newton force down and a 15,000 Newton force up. There will be some times when it will be important to get these forces lined up with the center of mass of the object. We'll talk about that later. But for now, you don't need to worry about where exactly on the car or the box and the ball. The main thing for the forces is the direction. And we also have now, as the car is going to the right, arbitrarily I set the motion 25 meters per second velocity to the right. So the force to stop the car, which would be, well, a little bit of air resistance, but also the friction within the brakes that are by the wheels. So there's a couple, but the main force that stops the car is the brake in the brakes itself. But it's a force that retards the motion. It's to the left. It's going to stop the car. If you try to use F net equals ma now, which is what we need to do, this is all problems about Newton's third law, basically. F net is F. There's only one force this time is F. So F equals the mass of the car, 1,500, not the weight, times A. Well, we have two unknowns here. Seems like it anyways, well, so far. But now we have to go back to our, not our bag of tricks, but our techniques and tools from last unit, and that is uniform acceleration, where as the car uniformly stops, we're assuming a uniform stop, we have a V initial of 25 meters per second. We're going to have a V final of 0 meters per second. We're looking for the acceleration of the car. S, the distance, the stopping distance is going to be 50, or displacement, 50 meters, positive to the right. We're calling that positive. And T, we don't really care about. But we're looking for A. And if you go back to your equations for uniform acceleration, there's an equation that says Vf squared equals V sub I squared plus 2AS. So if we plug in there, we'll have 0 squared is 0 equals 25 squared plus 2. Now we've already used 10 meters per second squared to calculate the weight, so I'm just going to use 10 again. I'm sorry. Check that. We don't know what the acceleration is. This is not free fall. We don't know what A is. We're looking for A. Times our S. So we have 2A times the S, which is 50. So the only unknown there is A. So you'll have 25 squared. Move that over. 2 times 50 is 100. Divide by 100. You get the acceleration. And the acceleration, if you do this computation, will come out negative, which makes some sense because the acceleration is going to slow the car down. We don't really care much about the negative right here, but if you want to be consistent, just put the A as a negative number, and then that answer will come over here, and then F will be a negative number. Bottom line indicating that it's a force that's retarding or stopping the motion of the car. So you can leave the negative in there. It won't be a big deal if you don't put the negative in there, but they're asking for the braking force. And the negative would indicate that it's opposite the motion of the car.